Hello and welcome. We're going to look at vaporization and vapor pressure. So imagine you take a beaker and you fill it full of a liquid, your favorite liquid, whatever it may be. And if you were to zoom in, right, you would be seeing the individual liquid molecules themselves, right? So these aren't bubbles of boiling, right? These are individual molecules, except they're probably not, circular in shape necessarily. So there we go. There are attractions that are holding those liquid molecules together, right? So that's why it's a liquid, right? If it were, no interactions at all, right, it would be a gas. And so all of these are holding the molecules together. And so the red things there, those are my attempts at those intermolecular forces. And again, this is the liquid phase. Now, if you look at the molecules at the surface, right, one of the interesting things is they're being pulled down, but they're not being pulled up again. So they actually don't have intermolecular forces on one side, they only have it on the other. So they act a little bit differently, right? So this surface tension here, you get this pulling of the water molecules or whatever they may be down. Every now and again, these molecules can get kicked up. So for instance, these molecules are constantly moving around and they can be buffeted. And imagine you're in the swimming pool, right? Someone comes from underneath you and surfaces, right? They will knock you out of the water. And so these water molecules, I'm sorry, I keep saying water, these liquid molecules can actually vaporize. So they can actually come and get knocked out of the solution and they can form vapor. So there's the vapor and there's the liquid. And anytime you've got a liquid, you've got a vapor above it, right? So it's just a gas. So the molecules are constantly moving at random, and every now and again they just get a nudge, right? And they get kicked out from the surface to form the vapor. Now this process is endothermic. So that is to say it absorbs heat energy. So why does it absorb heat energy? Well, it has to absorb energy to break those intermolecular forces, right? So when this molecule forms a gas, it has to break this and this intermolecular force here. So all these molecules, right, to break free, they've got to break this spider web of intermolecular forces. And when this process happens, right, so it takes in energy and takes it in from you, so it feels very cold. So if you spill some water on your hand and let it evaporate, it gets pretty icy cold, doesn't it? The rate of vaporization, so the rate at which the vapor forms, is directly proportional to the temperature. And why is that? Well, we know that temperature is related to kinetic energy of the particles. The hotter it is, the faster and more wiggly they're moving, and the colder it is, the more slowly and lethargic they're moving. So that makes sense there. It is also directly proportional to the surface area. So the more area you've got, right, the more chance you have of a molecule escaping. So it's simply a numbers game, right? So no one wins the lottery. Well, hardly anyone wins the lottery, right? But when millions of people play, someone's going to win. So individually, these molecules are very unlikely to escape. But when there's, like 10 to the 23 somewhere around the surface, odds are, one or two are going to make it now and again. And the other thing about the intermolecular forces, and this is sort of the thing that trips people up, is that it's inversely proportional to the strength of the intermolecular force. And you might ask, well, what does that mean? Inversely proportional. What that means is that as one goes up, the other one goes down. So when the intermolecular force goes up, the rate of vaporization goes down, and vice versa. So if the intermolecular forces go down, the rate of vaporization goes up. And we might think about what that means, right? So what we're saying is that the more tightly held the molecules are, right, the less vapor we will form. And the less tightly held they are, right, the weaker the forces, the more easily they can escape. So the higher the vapor. So what we find is the vapor and the vapor pressure, right, the vapor pressure we saw in chemistry 1 is the partial pressure above the liquid. Okay, so when the vapor rate of vaporization is low, the vapor pressure is low, right? When the rate of vaporization is high, the vapor pressure is high. So if you can think back to, like acetone, which is nail polish remover, if you spill it on your hand, it gets pretty icy cold, and it vaporizes very quickly. And what that's telling you is that it really has a low intermolecular force. Whereas if you spill water on your hand, it takes a long time to evaporate. And if you look at the molecular structures, right? So look at something like water. So water is a very small, tiny molecule. Acetone, by conversely, is quite a large, beefy molecule, at least compared to water. So let's go ahead and draw it in. And you might say, well, gosh, that's such a big molecule, right? Surely it's going to have high intermolecular forces. And that's such a dinky little molecule, right? Surely it's going to have low intermolecular forces. But by now you'll know that, of course, those correspond to the London forces, maybe. But this guy here can hydrogen bond. And so water can stick to itself through the hydrogen bond. And acetone, well, acetone certainly has a dipole moment. It has the ability to accept a hydrogen bond, but the hydrogens here can't be donated because they're not bonded to an electronegative group, so it can only accept. So it's like the sound of one hand clapping. So low intermolecular forces here. That means that lots of it can vaporize, so the vapor pressure will be high.